Thank you. Hello. Hello, everyone. So yes, I do work in Atlassian, and most of the time, my team and I work on the Jitsi org open source projects, suite of projects. So many of you here, especially in the free switch community, probably know about Jitsi because of the open source client that we were doing a few years ago. But then about 2012, 2013, we reoriented toward a more WebRTC enabled way of doing video. And currently, this is what we do, basically. That sort of Hangouts that you can deploy in your enterprise, in your communications group, or you can embed in your projects like companies such as Pi5 and JoinMe are doing. This is the open source suite of projects that we do. Now, an update since the last time that I was here. We currently have work in progress on the mobile version. That includes both Android and iOS. That will be fully featured. That is, have feature parity with our desktop versions. Support as many participants as you want. The possibility to switch in between them, to moderate your conferences. All of that is coming on mobile as well. And that, again, means that you can either use it directly or embed it in your products and make use of it that way. We also recently rolled out this component I really like because it's an example of how hackery can sometimes be an instance of perfect engineering. The Jitsi project allows you to basically take a Jitsi conference and either record it, and I'm talking about the full conference experience. That's not only the video itself, but also who was being focused at any given time. Shared document editing also gets recorded. Absolutely everything, chats, absolutely everything gets recorded. So this is also part of our GitHub project environment. Go and check it out. Or you can just try it out on as the live streaming feature on our Meet Jitsi deployment. This is a deployment that we maintain, free to use. Like there's a bunch of others out there, like Appearing and Talkie, pretty much the same concept. And Jitsi is enabled there, so you can live stream on YouTube your conferences, multi-party conferences, without needing an account or anything. Just go there and use it. Now, the cool thing about Meet Jitsi is that you can also use it in your applications as a readily deployed service. Rocket Chat, for example, I don't know if you guys have heard of Rocket Chat. It's a pretty cool project, sort of along the lines of Matrix, and we actually will be talking with Matt to do the same thing with Matrix, but they basically have deployable chat servers and applications for enterprises. By default, they come configured for a central server, and their default instance is configured to use Meet Jitsi. That took them pretty much a day of development to add multi-party video to their service. And obviously, you can also they didn't have to worry about deployment, but if you need to have your own video server for whatever reason, you can certainly do that with Jitsi. Now, this pretty much summarizes my community update. I'm going to now concentrate on the part that I came here to talk for. I hear there was earlier today a discussion about different ways of achieving video conferencing. And acronyms such as SFU and MCU popped up, obviously, as they always do in these conversations. So I'm going to talk about a bunch of evaluations that we did around technologies that SFUs often use in order to, to be efficient. So, quick reminder, an SFU is a video router. It means that whatever packets it gets from a user, it will forward to other users without changing the content of the packets. An SFU as a router does not understand how to create a picture, how to scale it. It doesn't do any of that stuff. The only heavy lifting that it does is potentially adjusting the encryption, because with the current state of affairs with WebRTC, end-to-end encryption is not possible. And we can talk about that actually at some point, but you have to transcript it. So this is really the heaviest that an SFU would ever do in terms of CPU power. However, looking at this picture, some of you might be thinking, this looks very neat in a conference of 3, but what happens if you have 20 people? Am I going to have 20 arrows going in each direction? The answer to that is yes, but really the question is, are all of these arrows going to be equal? Am I going to have 20 streams coming down at me at 3 megabits per stream? This is never going to work on mobile. This is never going to work on constrained video connections. And it won't have to work. That's the good news. So in comparison, the MCU, I'll go back to why you don't need all that bandwidth on an SFU, but in comparison, the MCU would just be an endpoint, and you would have a bunch of one-to-one codes, and everyone will be getting one stream down and one stream up. But the MCU would have to do a little bit more heavy lifting in order to get you there. So the MCU approach is chosen by FreeSwitch. We do the SFU. Both of these are very complementary. For example, you can bust your ass, and with an SFU, you're not going to ever talk to a video phone. So you need to have an MCU if you want to support the traditional life-size equipment, for example, or any of the stuff that you have deployed in your HD rooms. At that point, you have to use something like FreeSwitch, but if you are talking to browsers, on the other hand, or mobile devices, then really the SFU might be your answer. Here's the work that I'm going to talk about. It will be mostly about Simulcast. So who of you here know what Simulcast is? Okay, and out of these people, how many think that radio is somehow involved in this? Okay, because I got this note once. A very good friend of mine told me, hey, actually, when you talk about Simulcast, and people from my generation think about doing something simultaneously on TV and radio, that's Simulcast. Granted, for some people it might be. In our case, Simulcast is taking a picture, as you have a video stream going out of your computer. You take every frame, and you encode it in 3 different resolutions. You have one high quality, which will be 1080p or 4K when the time comes. Then you have something in the middle, typically 360p, and then you have a thumbnail layer, which is typically between 90 and 180p. So this is incredibly helpful. Oh, Dan, what did you do to me? Okay. This is incredibly helpful in applications that use that sort of layout, where you have one main participant showing on stage and a bunch of people that you're showing as a thumbnail layer. Now, it turned out that this layout became pretty popular a few years ago, and it just so happens that it is incredibly convenient to optimize the video transport for that layout by using Simulcast. The idea is that all these 3 layers that you have encoded at your sending endpoints, you're going to send to a video router in the middle, such as our Jitsi video bridge, or an SFU, and then that SFU is going to select either the high quality layer and transmit that to the receiver, in the case that they're currently on stage, or they're going to select the thumbnail layer and only send that to the receiver. So you end up using really just one HD layer, and everything else is just a thumbnail stream at 90p. Now, Simulcast has been around for quite a while, quite a few years, and the merits of Simulcast have been shouted over conferences for many times, but we actually realized, Boris and George from the previous slide, who are 2 incredible engineers. Boris doesn't actually look like that. He just doesn't want his picture going on conferences, but he just has a single nose. In case you're wondering. So Boris, George, and I thought, there's actually been a lot of talk about Simulcast, a lot of hype. We actually even went and implemented it. And never did we see measurements about how much exactly are you optimizing when you're using Simulcast, and what are your gains and what are your penalties when you're using Simulcast. So this is what we did, and this is what I'm going to talk about. So to begin with, let's look at the server. Now imagine an SFU, a video router, where every participant sends just a single stream, but that's your HD stream, and then that stream is being forwarded to everyone else in a conference. Granted, this is quite a mess, and this shows it. Basically, you have more people entering the conference, going from left to right, and in about 10 participants, you're already at 300 megabits. Of data that's going through your server. And that's quite a lot. The minute you turn on Simulcast, that conference is more than halved. in terms of bit rate. So that's clearly a pretty good gain. Now, the second thing that we wanted to look at is the CPU usage on a server doing simulcast compared to a server that doesn't do simulcast. And originally, when we saw the results, there was no difference. And we're thinking this doesn't make any sense. The heaviest thing that you ever do on a server doing simulcast or doing on an SFU is manipulating streams. It's encryption and copying bytes from one place to another. So why would we not see a gain when we enable simulcast, when we gain so much bit rate? Why would we not see a gain in CPU utilization? It turns out that this was an implementation issue, but since it's very likely for anyone implementing an SFU to encounter that same issue, I'm going to share it. Basically, when you have a sender, a browser sending data to us, this goes through our SRTP decryption chain. Then it goes into our input chain that will be resent to everyone. And in there, it gets re-encrypted for everyone and sent. Now, with simulcast, at one point we realized that all the streams that were being sent by clients, we were actually decrypting, even though we ended up not sending them. Not only we were decrypting them, but we were also copying them in all the right channels. And then when they got to the channel to a certain participant, we thought, oh no, actually we don't need to send that. So thanks for all the work, but it wasn't necessary. And interestingly enough, decryption wasn't even the biggest hit in terms of performance. It was just copying the data, making it available for every sender, and then just dropping it at the end. That was real mistake in terms of performance. Once we got rid of that, performance started to make sense again. And the yellow line here shows you the sort of performance that you get once you've done simulcast right on your server. Oh, and by the way, you might want to notice that if you're not doing simulcast properly at the server and you're doing all this copying that I just talked about, for 2 participants right there, for 2 or 3 participants, simulcast is even more CPU intensive than just doing regular routing, which makes sense once we understood the causes and after we fixed them. All right, so this is the server side. Now let's see how much gain there is from using simulcast on the clients. First of all, from a sender perspective, when you send simulcast streams out, you have your typical HD stream that you have in all these, that you have even without simulcast. So with Chrome, for example, that would either be 720p or 1080p or something in between. This, with 720p, goes at 2.5 megabits for Chrome. Your middle layer, which is typically at around 180, Yes, your middle layer is around 360p, goes at about 500 kilobits. And your thumbnail layer goes at about 150 kilobits. So you basically have 615 kilobits of overhead per sender, just in terms of bit rate, because you enabled simulcast. You might be thinking, well, this is more than if I weren't using simulcast, and it would be more if I were, I won't have this overhead if I were using an MCU. But then again, think about it. What is the difference between 2.5 megabits and 3.15 megabits? It's not big, really. How many users do you think can afford one and not the other? Not a whole bunch, I would say. So pretty much the same order of magnitude. Now, you also have potentially, that's something that we wanted to explore, an increase in CPU usage, because rather than encoding 1 stream and sending it out, you're now encoding 3 streams. And as we all know, with video conferencing, encoding is the biggest resource consumer. So that's something that we really, really wanted to evaluate, and let's see what happened. This is the CPU penalty, encoding simulcast. With red, we have non-simulcast. With blue, we have simulcast. As you can see, the difference in terms of encoding is really, really negligible. It's pretty much the variations that you have in CPU consumption are pretty much about as big as the difference between the two, encoding the 2 configurations. How is that possible? Well, to begin with, the lower two bit rates that you're encoding with Simulcast are really very low. Encoding 600 kilobits of video is really only a fraction of the amount of the resources that you need in order to encode an HD stream. Now, that's one thing. A second thing is that when you use a properly implemented encoder, such as libvpx, for example, that can support Simulcast natively, what it does is that it takes some of the calculations that it would have to do in order to do a video encoding, like the motion vector calculations, for example, and it only does them once for all the three encodings, and then uses them for all three layers. Now, that actually has a negative side effect, which we see on the next graphic here. This is traffic comparing a simulcast the high quality of a simulcast stream with 3 temporal layers with a non-simulcast stream. What we're comparing here is PSNR, which is sound to noise ratio, the quality of the image between the two pictures. Or in other words, we're trying to answer the question, is there a quality hit that you take because you're using simulcast as a receiver? Is your experience degraded? On the whole, they're pretty similar. The difference in decibels between the two, although noticeable and very interesting from a technical perspective, is not, although noticeable on a graph and interesting from a technical perspective, is not noticeable when you're using the application. But we still wanted to understand, why the heck do we have such a difference? It's supposed to be the same. The two HD layers are supposed to have exactly the same PSNR levels. When we looked into it, it turns out it was because of this optimization that was using reusing motion layers across vectors, and also because with Chrome specifically, when you're doing simulcast, your 3 layers have 3 temporal layers each, as opposed to your regular Chrome session where temporal scalability is not enabled at all. For those of you who do not know, temporal layers are basically just a way to look at your video stream where you're able to subtract different frame rates and render them independently. In other words, from a temporal layer stream, I'm able to take only 7.5 frames per second and only decode that, and I'd still get a coherent video picture. Then I can upgrade it with a second layer and say, now I have 15 frames per second, and upgrade that again to a 30 frames per second, which is another way to give SFUs more leverage in adjusting to your bandwidth and to your scenario. So once we removed the temporal layers from the simulcast flow, we got a similar behavior. So there was not so much jumping around in terms of the quality of the the levels of the PSNR. And once we put them on the same level, both simulcast and non-simulcast, we got the same behavior from the non-simulcast stream as well. Still, something unexplained here is that in this situation, simulcast levels are even slightly higher. So not entirely. This is something that we haven't been able to explain, but that's never something that you're going ahead in production. From a deployment perspective, this is the graph that you care about the most. Now, this is bandwidth usage on a receiver. And you can see that using simulcast starts already showing in a three-way conference where you're receiving 3 streams, you already have a gain of 50% if you're just using simulcast. And that keeps growing immensely. And one thing to observe here is that the non-simulcast, okay, so this is reversed. Blue is actually non-simulcast and red is simulcast. So the simulcast stream here pretty much behaves linearly, which would be the case with an MCU as well. Or in other words, the extra cost of using an SFU when you enable simulcast is almost negligible compared to an SFU from a receiver perspective, which again is mainly a point very important in order to address the argument of I could never use an SFU with mobile devices or anything on a constrained network connection. That's not true, simply. You could use an MCU for other reasons, compatibility, but bandwidth is not one of them, nor CPU-constrained devices. All right, so This is really the video transporty part of my presentation, and depending on how much time I have, I thought I might do a deployment part as well. Is there a clock in the room? Okay, I'm in 20 minutes. I have 5 more minutes? Okay. So in that case, I'll just do a quick plug. Everyone seems to be doing that. I'm learning from the best. So something that you guys might be interested in actually is when you want to do a deployment for Jitsi Video Bridge, which is the SFU that we are using, many people ask, sure, that works great. I've installed one server for my 100-person company, and that works great. But what if I want to provide my service to multiple thousands of people? I need to have high availability. I need to have a very reliable failover. I need to have auto-scaling behavior so that I don't pay a bunch of money to Amazon. How do I do that? And here's quickly what we're doing. We thought that that might be useful to other people. First of all, here's a way to look at our stack. You have a signaling entity on the top here that's called Jitsi. This is basically our conference orchestrator, and that manages Video Bridge. Your browser connects through our signaling channel, the top right corner of this square, and to the bridge directly when it comes to sending and receiving video. So our conference orchestrator, which is Jitsi, supports natively scaling up bridges to as many as you need. So typically, when you deploy that sort of stuff in a network in a highly available environment, you would put those things together, and you would put them on Amazon, and you would configure them together in an auto-scale group, and you would just have them grow by bandwidth. Jitsi would handle that without a problem, and this would give you that sort of configuration where you have one signaling stack at the front and a bunch of bridges at the end. Any bridge falling down, any bridge being added or removed, that's handled by the Jitsi components at the front. Now, you could still ask what happens if that Jitsi component fails, or the Nginx server, or the Prosody XMPP server that we're using to talk to it. Well, that's a great question, and that's why you take this entire shard and you deploy it multiple times. And in order to use those reliably, and because you don't want to have conferences be split over the two deployments, there's a very convenient way of doing session affinity in HA proxy that allows you to store conference names in a stick table. So you put a bunch of HA proxies in front of those, and that allows you to distribute your conferences reliably and statefully across your shards, so that if a shard falls, your HA proxies would move it to the would move all existing conferences to the other one. If new people join an existing conference, they would forward it to the right shard. So I just wanted to give you a quick overview of that. If anyone here is interested in deploying video through Jitsi Video Bridge and would like to learn more about this, just look me up after the conference, after the talks today. And with this, I'm going to cut it. Are there any questions for either this part or the simulcast evaluation? Is anyone still awake in the room? Yes. Are you saying you're awake or you have a question? Both, okay. Could I describe each piece here? Okay, so the Nginx server is something that we just use to talk to browsers and to take their BOSH requests. Basically, this is where you load your content. Granted, most of it might actually be on a CDN. This is where you establish a connection to Prosody, which is our XMPP server. We use XMPP for all signaling. It was just a very convenient option. Actually, people that are using Jitsi Video Bridge, such as Join Me and High5, have their deployments without XMPP, so that's just the way we chose to do it. So Prosody is the next XMPP server sitting directly behind Nginx that provides it with web access. And Jitsi is the thing that creates conferences. So as soon as you enter a specific room, it will go and create all the channels that are required for that conference on the video bridge. It would open all the ports, take the DTLS fingerprints, exchange them with the clients, and all of that stuff. And then the video bridge itself here is the bottom layer, the 4 boxes that we see auto-scaled. This is the video router. This is the part that takes video streams from all clients and then sends them along to all receivers in a conference. Does that answer your question? Great. Sure. Any other questions? Yes. Sure. So from a user perspective, there's nothing to do. There's no flags or anything like that. Simulcast is just, when it's supported, it's supported. Now, from a developer's perspective, on Chrome, supporting Simulcast happens through a sort of hackish mangling of your SDP. You basically create an offer. We receive an SDP that contains the description of your video stream and the source, the SSRC. So you basically just go and replace that attribute that contains the SSRC with 3 new attributes, with 3 new SSRCs that you just invent. And you set that using set local, set remote description, and the browser says, oh, 2 new streams appeared. They must want me to do simulcast. So that's how Chrome handles it. Once you do that, you don't have to do anything else, because the actual adaptivity is handled by Chrome. Like when it has enough bandwidth, it would send all 3 of them. When it detects that it doesn't have enough bandwidth, it would drop the highest quality layer or the middle one. So that part it handles natively. So that part's pretty cool. You really don't have to worry about it. On Firefox, the second part is the same. So they still adapt automatically to your available bandwidth, but the SDP is actually standards compliant, so they just do it according to the ITF drafts. In all fairness, the Chrome implementation existed long before the actual drafts appeared on the ITF, so this is not an attempt from Google to do their own thing or anything like that, and they'll probably go around to support the same way as Firefox. Other questions?
Any other questions? Big
Yes.
round of applause. Oh, one more. Go ahead.
Hold the applause, though.
Hold the applause.
Yes. I'm sorry, for the Android and iOS clients, what was the question? Yeah, actually, it's a React Native client, so it's the same code that runs on both. There are some minor differences in the native parts, though. But yeah, everything is available on GitHub. And yeah, we've actually been extremely happy using React Native for this project. So we're very happy with the performance. We're very happy with, we've been able to reuse our entire signaling stack without a single, well, there were a bunch of changes, but I mean, there's no fork currently. We use the same stack as we use on desktop. So using React Native has been pretty cool in helping us achieve that. All right, now you can get the applause. Thank you.